discussion that was this morning about, I think Melissa was particularly concerned about what's the uncertainties in reconstructing astrophysical properties that then go into direct detection and other things. So the idea is that my problem in this moment is saying that we all want to reconstruct the parameters of a certain Lagrangian beyond the standard model, and whatever this fundamental physics, this fundamental model that I have, it makes some prescriptions for some phenomenological quantities, which is what we want to observe. Okay? So we have a scattering cross-section of the dark matter with the baryonic sector. We have self-annihilation cross-section of the dark matter with itself. We will have an assorted cross-section for production at collider. And all these proceed from whatever I have in Lagrangian. But the interesting thing is that if I want to play the game and have a suitable candidate that can comply with all of that, I can get this from direct detection experiment. I can get, or the sun, neutrinos from the sun. I can get this from indirect, and I can get this from collider physics. Somehow, okay? Then I must somehow then have under control whatever is happening inside the actual experiment, okay? But the thing is that if my model is such that I have to combine all this information, whenever I want to get information on this, even though one of the three does not depend on anything that comes from the sky, and it just depends from what is within my experiment, the other two do depend on what comes from the sky. And what comes from the sky, I don't mean the possible foreground, background, or things that I have to clean, but actual information that I can access from the sky. Okay? So that is to say, if I'm looking at direct detection, the rate of events is going to be a certain combination of the cross-section that I want to measure, multiplied by the local dark matter density. Okay? The dark matter density around the sun. This is not the background, this is not a foreground, this is not what I have into my detector, it's just a quantity that I have to know. Okay? Same thing with indirect. The flux that I'm going to observe is going to depend, in order to make sure that I'm observing a dark matter flux, I have to remove all the foreground and background. This is something that is going to be discussed tomorrow, has been discussed today, it's going to be discussed yesterday actually. But intrinsic flux is going to depend on something which we will call J. I don't like to call it like that, but it's certain function of the dark matter density in the target, or the dark matter density squared, depending on what you look at, and it's going to depend on the quantity that you want to know. All right? Everybody agrees on that. So that means that even in the best of cases in which I can remove all the foregrounds and backgrounds appropriately, etc., 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 I know everything what's going on in within my instrument, within my detector very well. If I want to reconstruct the properties of this, I still depend on something, this and this, that I don't know exactly what it is. And that I have to reconstruct from astrophysics. Yes, Nancy?
Just to add that we have to also add velocities.
Yes, indeed. I'm not even touching that because it's even more complicated. So it's adding a degree of complication, but it's totally true. This is the local dark matter density multiplied by the dark matter velocity structure. Okay? A function of the dark matter velocity structure.
Yeah, and the nuclear structure functions and
Say again?
and the nuclear structure function.
But
that's what I call within my instrument. There's something, the nuclear structure function. It's not astrophysics.
Yeah, nuclear physics.
It's nuclear physics. Right now, I'm just caring about this is something I'm factoring out. Say, even though you have that part completely under control, which, as you're saying, I don't think you have, but on the top of it, you have something that comes from there. Okay? That's the object of my talk. No, we can agree that maybe the nuclear structure function is more important, but that's not going to talk.
These two things you cannot directly decouple them, right? You only with the assumptions your causations is a velocity independent, something like that.
Of course, but that adds one layer of complication to what I'm saying. So if at the end of my talk you're going to be confused as a proceeding from your observation, you should square it up. Okay? Now, how do I know the dark matter density? So let me concentrate on the dark matter density around ourselves, around the sun, and how I'm trying to access that quantity observationally. Because And one thing that people have done, what people do to compare experiment with experiment, you use a benchmark number 0.3, which is fine. You have 0.3 and not 0.4 for historical reasons. It's totally fine to compare one experiment with the other, provided that the velocity function is the same, etc., etc., etc. But if you want to put all this information together to actually constrain the actual parameters of a Lagrangian, this thing is coming from this, and this is the real data. It's not a benchmark number. It's the real data. We need to know exactly what density is around the sun. And if it's a quantity that we get from observations, we have to include the uncertainties that come from that. Okay? So the object of my talk is how do we get that number and others, and that number, if you want to run it into your analysis, is not 0.3, it's a certain number with a certain uncertainty. Okay? And the uncertainties are a lot. So people know that, but we've been trying to quantify that. Okay? So my concern, and I'm going to show you what my concern is. So there are two general methods to tell what's the dark matter density around the sun. So this is our galaxy. This is a bulge, which is not a bulge because it seems that people don't agree about the existence of a bulge on a Milky Way, but I like to call it a potatoid because it has a very strange shape in the center of the galaxy. It occupies more or less the center of 2.53 kiloparsec with a gravitational effect up to 4 kiloparsec. That's the disk. Of course, you're looking at the disk phase-on. If you were looking at it, it would really be a disk, which can be divided into thin and thick disk. This proceeds from observations, not from a priori modeling. Okay? And one thing that we do is that we know that the Milky Way is a spiral galaxy. Of course, there is an overdensity, which is the spiral arms. Slight overdensity, which is not really going to change things. And what people do is, you know, the rotation curve method. It's one of the two methods to tell the mass of a galaxy. You look at the rotation velocity. That means that the galaxy is rotating differentially. So this is bigger. This becomes flat, more or less. Here is smaller. Okay, and proceeding from Newton, you can say, okay, if this is the velocity that I observe, I can invert and get the velocity is proportional to g. Okay, and that means that if I can measure the velocity, I can measure the enclosed mass. Okay, now fair enough. This is not going to tell you anything about dark matter a priori. It's just going to tell you how much mass is contained within each point. At which point you say, okay, but look, well, there are problems in observing this, first of all, because I'm not sitting in the center of the galaxy. I'm sitting somewhere off the center of the galaxy. So what I'm actually measuring is the line of sight velocity of this, and I have to reconvolve it to the velocity of the center of the galaxy, with respect to the center of the galaxy. So first of all, I depend on two observationally determined quantities, which are my distance from the center of the galaxy and my velocity with respect to the center of the galaxy, okay? Which are rho naught and v naught, okay? These things you can get from different observations than these, but they're observationally determined, so they carry an uncertainty. Now you can fix them, but they carry an uncertainty, okay? So every time you have this curve, you don't have this curve, you will have a slightly different curve every time you change these parameters, okay? Second thing, okay, right now, say that I fix this, and I get the velocity, so I know the enclosed mass. But if I want to tell something about the dark matter, I have to subtract the visible matter somehow. And what I do, I observe at a stellar field, baryonic field, so stars and gas. And I do proceed from observations. I do actually have a determination of the density of stars in the galaxy. Okay? And so it turns out that you can look at something like this, so within something like 3 kiloparsec is a bulge, so it's sort of a constant density that goes down. And then I have a disk, which sort of kicks in, and it's another, and this is something like 10 kiloparsec, okay? Now again, this is a density that comes from observations. So I observe a certain type of stars, I can infer the mass. So first of all, I will have an analytical approximation about what the density is, but the other thing is that this is one set of observations, it's not the same, but they carry uncertainties, and they also carry statistical uncertainties, okay? So that means that if I want to reconstruct the unexplained mass, I have to construct a rotation curve that comes from here, that it's nothing else than the forward of this equation, and it will carry huge uncertainties. Okay? So whenever I want to get the missing component, and that's something we're supposed to do, assuming that you know the symmetry of the stuff that is within, etc., 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 I will have a purely statistical uncertainty that comes from the combination of this and this. Okay? And it's purely observational. Okay? It's the problem. So let us say that I want to fit an additional density component, which is the dark matter. So I say that the missing density is something that goes like a power law, alpha, a certain normalization that I will call rho naught, and a scale radius. I can fit this, I fix this, I can fit alpha, I can fit rho naught, and I will add another component here, and I can fit the two missing components. So I can renormalize it at the sun, and that's what goes. There will be a statistical uncertainty associated, okay? So from this it proceeds that the number you can get, and that's rho naught, people put it 0.3, but let's say 0.4, plus or minus a statistical uncertainty, which proceeds from that. Everybody's fine with that. Now it turns out that I already told you about this, which I haven't included, okay? So there will be another uncertainty that comes from certain things that I have completely neglected, okay? So there is another uncertainty, which is some sort of galactic parameters. And there is another problem, which in my opinion is even bigger, is that this density reconstruction of the stellar field is not univocal. So Alison was mentioning it's not clear whether there is a bulge in the Milky Way. Well, when you classify stellar density, you do it on the basis of certain stellar populations. You must assume belong to some relaxed component or not. So, and same-ish thing for the disk. So one thing is normalizing the stellar mass with an observation that carries a statistical uncertainty, so it's well posed and you get a statistical uncertainty. But the thing is that you have n distribution of density alternative to each other. You can't average them out, they're just systematic. You don't know exactly what the field is. So you will not have one curve like this, you will have n curves like this. Now, it turns out that, first of all, within the Milky Way, none of these alternative curves fit the observed data decently. Like, they fall very much away from 5 sigma at basically any radius beyond the sun. So one thing is that it really looks like there is a missing component, basically at any radii from 6 kiloparsec on.
Sorry, 1 second. So these curves differ from the S0 parameter? What is the difference by...
No, these different curves are just alternative morphologies for the visible component. I just don't know exactly what the distribution of stars is.
Okay.
So you have different functions. You have, so
Is
say
it
that
because it's so difficult to measure from inside the disk, or?
it's because for the bulge, it's because it's well, yeah, it's you have either optical or infrared measurements. You don't know, if you pick slightly different population of stars, you get a different distribution. You don't know what to associate them to exactly. So the point is that whichever the reason is not agreed upon, which is the shape. So you're not allowed to make a choice unless you really know what's going on. And so you will have 1 stellar density, 2 stellar densities, 3 stellar densities. And all of these different stellar densities will give you a different result for this number. Each one of them will carry a statistical uncertainty that proceeds from the normalization of this function, so that's well posed, and it carries an uncertainty given to some galactic parameters which are R naught and B naught in this case, so our own velocity with respect to the galactic center that people don't mention, but they are there. Okay?
So is the problem that you have several different models and you're trying to find
I
the
don't
best
know.
one that fits your stellar distribution, or is it I have several stellar distributions and I'm trying to fit individual stars? I'm trying to put
No, you have stars. You have an observation of a given population of stars, and you try to reconstruct the density function. But the thing is that if you pick a slightly different, if you pick a different stellar population, you will get a slightly different density.
So what do you mean?
So ideally, you would just want to map all the stars and get distribution of the mass, which you can't do. So it's not a conceptual problem, it's just a practical problem, but it still affects.
No, but when you say pick a stellar population, is that pick from a catalog of, pick from a list of models, or pick from?
No, from the actual stars.
From the
Yeah.
stars.
Okay, so certain, I don't know, I don't remember which bright giants are used to track thing in the bulge. The different groups, they use different populations of stars. The thing is that it's extremely difficult to make a choice, and this reflects on your results.
It's not just for the bulge, or you're talking in general?
It's two separate things. It's separate things. One separate thing for the bulge and separately for the disk.
So it's just that, so the problem is that the observers don't agree on which populations of stars belong to the disk, for example, or belong to the bulge, and there are different groups giving different results.
Yes. Something of that kind.
And when you said that none of these possible distributions fit the data, is
No, I didn't say that they don't fit it. No, what I meant
fit the
here.
observation, so
No.
that it is for the rotation curve.
Yeah. So this is another thing. Okay.
So
Good. Thank
no
you for
matter
asking.
what, we need dark matter.
Exactly. So
Okay.
it's in any of these possible configurations. I don't call them models because it seems like you've been modeling them. I call them alternative baryonic morphologies. But each one of them, if you take each one of them individually, all of them fall short of explaining the rotation curve. There is absolutely no way to explain it. If you take into account the statistical uncertainty, if you fit, it's a parameterless fit, you just fit one curve to the other with uncertainties, one set of data to the others. It doesn't fit, and more than 5 sigma, okay? It's just very bad. You can see it by eye, but you shouldn't do it by eye.
What I mean, the conclusion is then to, with respect to the dark matter density, if I go through the different curves, or I come into that.
I'm coming to that.
Okay.
But
Yeah, well, just really quick, the statement you're making that we can't really tell the baryonic density inside the bulge and part of the galaxy. This is partly what you're saying is there are certain like high mass, very bright stars that are used as tracers of the,
Yes.
of the general stellar population.
absolutely.
But then there's a separate question as to whether the mass distribution of stars in the bulge is the same as out by us, which is often used.
No,
as
that is separated.
Well, that-
We compute one bulge, we take one bulge, and we take disks.
No, I don't think I'm disagreeing with you. What I'm saying is that in the bulge, they're extrapolating what the baryonic mass is based on a particular set of tracer stars. Is that correct?
The distribution, not the mass. The mass, we renormalize everything to microlensing, and that's sort of well posed.
Sure, the distribution, right? So
The
your
distribution,
stellar
the morphology,
uses-
the morphology.
uses these tracer
Yeah.
stars.
So my concern is not about the normalization. My concern is about the alternative morphologies which I can't average out, or I can't, at least with my limited mind, I can't figure out how I can mix one to the other. The normalization doesn't worry me, it's just a factor. And the statistical uncertainty is well posed. What worries me is that state of the art, I can't grab an information about one morphology, so let me do this just for the sake of clarity. I will have one morphology, I will have morphology 2, and I will have morphology 3, and so on and so forth. Okay? So, and it was being said, every time I fit the dark matter component on the top of each of these, I'm going to get a different result. Okay? And each of these results will carry a well-posted statistical uncertainty, but they're incompatible one with the other, or at least I don't know how to figure out how to put them, to pick one or the other. Let me just get to this. So this is the actual data for the rotation curve, and this is a convolution of the central lines of each one of these alternative morphologies. So this is not a statistical uncertainty. It's just each one of those lines overplot on the top of the other. Okay? And then for each one of these lines, you can fit it. So this is where these lines come from. This is the bulge. This is the disk. You have different morphologies. You have the gas, and so you have m bulges, m disks, 2 gas, and you do one by one. So you don't mix them up. You do A1 alpha, A2 alpha, etc., etc. So what happens is that this is the 2 sigma region for rho naught, and in rho naught and alpha for each one of those morphologies. Okay? So they do shift. Okay?
No, I wasn't saying they don't shift. I was just saying where are these uncertainties and what the central density of stars, where are they coming from?
Yeah, no, I'm sorry. I was in that moment. I wasn't addressing you.
Oh, okay.
I was just. I'm concerned about the fact that if I was just to change normalization, which we have done, you just move each one of these points up or down. Okay, and if the measurement is different, you might change the size of the error bars, but to all of them. The fact that they spread quite a lot, it's my concern. Okay, and I don't know how to change this. I don't know how to put all the information that I have about stellar models together to say it's one or the other. Now, for what concerns this reconstruction, this is a problem, okay? Because the fact that I have different R naughts and gammas, so the slope of toward the galactic center, which is another matter on itself, is actually changing, if you want, the J factor toward the galactic center, okay? So you're going to have an effect from the fact that you have an irreducible systematic given by the morphologies, and on the top of it you have something which is not typically considered, which is distance and velocity with respect to the galactic center, our own velocities. So you have something which is systematically reducible, and then you have this effect, which I was mentioning before, which also shifts things. So whenever you're adopting R naught to make an actual analysis in a given parameter space of new physics, not to compare one experiment with the other, that you can do. You're just normalizing all the same way. When you do it all together, that's a problem. And that's not even mentioning what Nassim was saying, velocity distribution.
So there's this other way, I guess, of measuring the dark matter density using local stellar data?
Well, we don't consider that because, well, we obviously take that into account. We know it exists. The point is that the uncertainties that you get in the local stellar data, it's huge. So if you look at this, I might have a plot.
This is an independent way, right, of trying to get at the...
Yeah, but it's not going to tell you anything because the error bars are not given from the stellar density, from the local measurements, is like this big. That's the statistical uncertainty of, is something like much bigger than the statistical uncertainty that you get from this.
But it looks like your systematic uncertainty is about that big, just because you have so many different...
I understand. Yeah.
So where do they sit here? My impression was...
No, they are all...
So,
There's two facts about this plot. The first good thing is that the central values of these all sit somewhere around 0.4-ish, okay? 0.42 or 43. So if you care about the central values, that's actually a very good thing. Okay? We agree on the fact that more or less the local dark matter density is something like this. Phase value. And that's actually more or less the value that you find with vertical motion of stars, that by itself have a bigger statistical uncertainty.
isn't it a little bit... I thought... Okay, maybe I'm not remembering the number right, but I thought it was closer to 0.3.
No, that's the number that is historically used. The first 0.3 is the number that's historically used because if you take an NFW of the central mass of the Milky Way that was accepted 20 years ago and you fit it, you got 0.3.
I'm thinking of a paper by Joe Bovee from 2012 using just the vertical motion stars. I thought of
The paper from 2012 of Joe Bovee, if I'm not mistaken, is reconstructed the density toward the center, and I don't think it's closer to 0.3. If you adopt this method, well, I might have the plots.
I thought those were stars above and below the galactic plane.
Yes, and it's a function of the radius also.
But then it's look like
Yeah, these are
around
local,
the
just
solar
a few
eclipse.
kiloparsecs of stuff.
Yeah.
Yeah.
This is plot of Justin.
I have it in the present. I just erased it.
I know that's
It's not what we're looking for. Here. Okay. So these are historical values. And the y-axis doesn't mean anything. Okay? It's just separating one measurement from the other. This is the historical one. So I'm not concerned about the central values. I'm just concerned about extracting as much information as I want, as I can from this. And especially about the fact that even if you want to use R naught from the vertical motion of stars, that has a huge statistical uncertainty, but still it doesn't give you any information about gamma. slope. So my question is more conceptual than practical, and you can still run your analysis, but when you do it, you have to take into account the fact that you're extremely limited.
What is the red line?
The red line is 0.3. The red line is the historical value. It's just to guide the eye. 0.3 is the historical value, but the first systematic reconstruction fitting to the rotation curve was done by Julio and so by Piero and Riccardo, and it's this one. Okay, and it's not 0.3, and we find more or less the same value. Okay, so.
But which data is more model dependent? It just means that everything just taken from the
Say it again?
conditions. Which values? Yeah, if you see the laser table just together with these figures, the figures you show.
Yes.
Yeah, and then you can see so many numbers. Some of them depends on the simulations.
That's
Some of them depends on
No,
rotation
it don't
curve.
depend on simulation. No. That's not dependent on simulation. So let me get to the point. Thank you very much for the question, because this is exactly the thing that motivated Miguel and myself in embarking a long thing. So if you look at this plot, it looks extremely confusing for one reason, in my opinion: the size of the error bars.
Yeah.
It's not the central value. The size of the error bars doesn't mean anything to me. It's one is huge, the other one is tiny. Which one is a statistical? Which one is a systematic? You have no idea about it.
But some of them is assumptions. Some of them.
Absolutely. So if you're taking that, that's what was being mentioned today. If people take plots and use them acritically, you don't know what you're getting. So what Miguel and I did to achieve these results was to go systematically through the rotation curve data, purge the rotation curve data, things that were fishy or univocally not accepted anymore from the community, purge the data that were used twice. That was on one thing, on one hand, the rotation curve. Then, this number of Piero and from Catena and Julio, it was definitely a benchmark number, but they didn't use an actual different morphologies. They used one, and I don't remember exactly how they normalized it. It was good, but as you can see, the statistical is small. But still, that's clearly not representing the uncertainties that you might have. Okay, so what we went, it was through a systematic classification of all the uncertainties to try and get something that you can believe. And in fact, the first of this set of papers was just validation of the null hypothesis. Do every one of these single alternative morphologies fit the rotation curve or not? Period. Is there any dark matter or not? And where does the null hypothesis fit? It was a very simple question.
I remember Julio's paper is they have a format of this rotation curve, right? So these velocity distributions. They choose either Maxwell.
Yeah, I mean,
choose
our results are absolutely by no way in conflict with those of Julio and Al. Now, my point is different. My point is, whether you believe the result of Piero or someone else, our compilation is more extended, whatever. Piero would have done the same if he had had the time, I'm sure. The thing is, now that you have this, and now that you know that you can't just pick one value if you want to reconstruct that, if you want to do this, I mean, if you just want to use a benchmark value, I'm fine with that. I'm just not going to cite your paper because I know it's going to be wrong to a certain extent. You can use 0.3. The thing is that there's one thing that I wasn't mentioning. Those numbers just shift because I'm shifting the velocity of the sun. And this is just for that spread. And this, we know it's there. And Piero and Riccardo didn't take it into account. Well, they know it exists, they mention it, but this number was not done. So an exercise that we performed with Nassim, Miguel had already left academia by the time, my student and Francesca, was to say, okay, all this stuff changes the constraint in the parameter space. Does it really change them, or is it just a lot of hocus pocus, but practically the results are very small? And it turns out that the results are not very small. So we chose some model where you can clearly see where the parameter is coupled to the astrophysics. In this case, if you can see, the scattering cross-section is just one coupling with the Higgs. And so these are the constraints. This was the Lux, well, I don't remember which, yeah. And so these are the constraints, and this is what happens if you pick one of our morphologies, one of them, you put R naught as from those morphologies, and you can see that there is a different shade of green. No, you can't. Well, barely. That's because that's the statistical uncertainty. So it almost makes no difference, okay? If you're including the statistical uncertainties, so everything that arises from these uncertainties and these uncertainties on one single morphology, you can barely appreciate it and probably doesn't really make a difference. But if you start including the effect of the different morphologies of the galactic parameters, you screw up real
distance
from the sun are not and be not, you are really changing the constraints. Now, one good point is that, as was being mentioned today, you just your constraints shift. On one hand, you will say, okay, there is a good point to this. I know that if I take the worst case, that's not going to move. Okay, the one that gives me the least constraint, that's a benchmark. I'm not going to move away from that. But again, if you're ruling out a certain point, you're likely to just based on a central value of something where the statistical uncertainty are not. That's going to be a problem. So the question is there any way that we can marginalize out these are not and be not? We're going to get some information from Gaia, but it's not going to happen tomorrow. So this is likely to shrink a little bit. That's not likely to be shrinking. And this is a very simple model.
If I understand correctly, these galactic uncertainties are conceptually different to the morphological ones.
Absolutely.
In the sense that you could say R0 is some value with an associated uncertainty, and you can imagine propagating that through your calculation. So if you observe dark matter, you could propagate that uncertainty all the way through to your measurement of the cross-section. Whereas, if I understand correctly, you're saying these morphological ones, you don't know how to assign an uncertainty between these different models.
Right. And you go to the sample and you tested a finite small number of morphologies, and that could be of your space.
Well, and same thing if you're including the slope. Now, this is how the favorite region, if you interpret the galactic center excess in terms of dark matter annihilation, would shift. And in that case, the problem is given by the morphologies. The biggest problem is given by the morphologies because they really affect the slope toward the galactic center. Not that I believe in the galactic center. If you interpret the galactic center excess as dark matter annihilation, it's going to change things.
So in that case, when you're interpreting the galactic center axis, if you assume the galactic center axis is from dark matter, you have another measure which is gamma.
Yeah, you've measured gamma.
Absolutely. This is just to mark the point that there is an effect on the slope.
Yeah.
Okay.
These different morphological models you don't necessarily treat them on, you wouldn't necessarily think of them on an equal footing, right? Presumably some of them fit the data better, or
Absolutely.
presumably you have to go one step deeper into the data and be fitting not just the rotation curves, but also these.
They do. Yeah, you would have to make a model screening of those better and saying who you're trusting more for their work and what's. For instance, there is one thing. The disks, I tend to believe one disk best because it's the last disk model that came out. It's made by Bobby and Ricks that are extremely careful persons. So I tend to prefer that work to one of 20 years ago. Okay. But that's probably just for sociological reasons because I know these persons, I know exactly what they're doing.
You'd like to have a weighting on models that does not depend on
On myself, exactly. It's not my psychological pride. So that's exactly the reason why we went through the pain of putting together all the morphologies, because sometimes there is a strong personal pride. When we went through the data, actually, the rotation curve data, that eventually they don't make a big difference, but the fact that astronomy is by itself one of the most ancient sciences, it makes one of the most historically eradicated enmities history. Like one group is just not citing the others for no apparent reason whatsoever. They probably fought in Cambridge 300 years ago, and then the descendants of that person is just deciding not to quote that line of thought.
So, could you come up with like a hyper model which somehow encompasses all these morphologies and then try and fit the data?
I was hoping the statisticians would do it for me.
Okay, sorry. Yeah.
I already went through the pain of putting together all the data. So this is the problem I wanted to add to the pod today, but then I have my own problems that I was hoping the statisticians would try and solve. Related to bumps in the rotation curve we discussed with Alex, related to other problems that we're trying to solve. Okay, now, well, first of all, I'm fitting to these like a perfectly spherical model.
Before we go into this, how long is this discussion going?
2 minutes?
Okay, 2 minutes is fine.
Okay.
You're at -4 right now.
Yeah.
It's the first time I screw my talk time in probably 12 years.
I'm happy to allow 2 minutes, but Yeah, just
To 2 minutes, 2 minutes, just to mention. There is one problem we're trying to solve, and this is probably something for statistics too. I am taking, so I'm just fitting spherically a dark matter on the top of these, and taking our knots, and then saying, okay, that's the true value, but it changes from morphology to morphology, etc. But actually, I don't know my method of fitting, how accurate it is. So I don't know how the number that I'm getting from each of these fitting procedures is the real number. I don't have mock data. I don't have a fake realization of the galaxy in which I can test my method, the Milky Way. So this is another thing that we're trying to assess, and that's intrinsic. So there's a lot of things related. There's something minor, for instance, the bin by bin, the baryonic uncertainties are correlated. That's something simple when you won't get away. A few things I wanted to just throw into the pot and see if someone wants to come and talk to me.
Okay, let's thank Fabio. Yeah, next we have Francis.
While you're coming, can I play a game with you? Someone mentioned it, modified gravity. So, if you wanted to fit these data, would you prefer the black, the red, or the blue?
Not the blue.
Not the blue.
The blue looks terrible.
The blue looks terrible.
Well,
And the black?
The black is brilliant.
But the blue looks terrible. So these are the best fitting of Newton, generalized NFW, and this is the best fitting of all the modified gravities that I can find. That's the best fitting one. And it's calibrated on spiral galaxies. It screws really bad with clusters. So this is the best they can do with the Milky Way.
the red is also kind of terrible.
I mean, nothing goes well.
The red is not great either.
Is there any water too?
Do I stop this
Yes.
recording and stuff?
You want some?
No, I don't mind. I'm good.